It takes an astounding 26 weeks to construct a microchip, each featuring as many as 100 layers. Within these layers, billions of transistors are carefully packed into a space no larger than a fingernail. These tiny masterpieces of engineering power our increasingly electronic world. So how are these complex, minuscule devices actually made? Stick around as we delve into the intricate creation process of the microchip. Don't worry, we'll break everything down as simply as possible for you. Preparation. It all starts with silicon, the cornerstone element in microchip manufacturing. Silicon is a plentiful material found in sand and rocks, but the transformation it undergoes to become the foundation for a microchip is anything but simple. The raw silicon is initially purified in furnaces at temperatures exceeding 2000 degrees Celsius, eliminating unwanted impurities. What comes out is metallurgical grade silicon, which still contains some impurities. The next step is to further purify this into electronic grade silicon through a process called the Siemens process. Here's where it gets interesting. This method exposes the silicon to repeated cycles of chemical reactions and distillations, reducing impurity levels to less than 1 part per billion. Yes, you heard it right. A whopping 99.9999999% purity is achieved. This ultra-pure silicon is then subjected to Czochralski growth, a process that involves melting the silicon and drawing it out slowly to form a cylindrical ingot. In simpler terms, we're making a silicon crystal rod. This ingot is then sliced into ultra-thin discs, known as wafers, using high-precision cutting tools. Each wafer serves as a blank canvas on which intricate circuits with billions of transistors will be imprinted. These wafers, often as thin as a sheet of paper, are then polished to a mirror-like finish, preparing them for the complex processes that follow. Doping and oxidation. With a pure silicon wafer ready, the next step in our microchip process involves some purposeful contamination. This stage is known as doping, where the silicon is infused with tiny amounts of other elements like phosphorus or boron to alter its electrical properties. You see, silicon by itself isn't a good conductor of electricity, but the doping process turns it into a semiconductor, making it easier for electrical current to flow in a controlled manner. Oxidation comes next. When you hear the term oxidation, you might think of rust or decay, but in microchip manufacturing, oxidation is a critical step. A wafer is exposed to high temperatures in a controlled environment, causing a layer of silicon dioxide to form on its surface. This silicon dioxide layer acts as an insulator, providing a base for building complex electrical components. For those of us who aren't electrical engineers, think of doping as adding seasoning to a dish. It enhances the natural properties, making the final product much more effective. And oxidation? It's like adding a layer of non-stick coating to a pan, setting the stage for what's to come without allowing unwanted reactions. So, in doping and oxidation, we are essentially laying down the rules of the game, defining how electricity will move and interact within the upcoming circuits. Photolithography. After the wafer is primed through doping and oxidation, it's time to imprint the circuit patterns. This is where photolithography comes into play, a technique that might sound complex, but essentially means writing with light. In this stage, light-sensitive chemicals called photoresists are applied to the wafer's surface. Once coated with photoresist, the wafer is then exposed to ultraviolet light through a mask. The mask has patterns that define how the circuit will look. When the light hits the photoresist, it undergoes a chemical change that makes certain areas soluble in a developing solution. To put it simply, the light sketches the circuit design onto the wafer. After this exposure, the wafer goes through a development process where the unexposed areas are washed away, leaving behind a precise imprint of the circuit. This pattern acts as a guide for the subsequent steps of ion implantation and chemical etching, which we'll get into next. With the circuits mapped out, the wafer is one step closer to becoming a functioning microchip, capable of powering the electronic devices we can't seem to live without. Etching. After the patterns have been set through photolithography, it's time to carve them into the wafer's surface, and for that we turn to etching. Imagine etching as sculpting, but on a microscopic level. The idea is to remove excess material, leaving only the design imprinted by the photolithography process. There are two main types of etching: wet and dry. In wet etching, the wafer is submerged in a chemical solution that dissolves the unwanted areas. While effective, it's a bit like using a chisel. It gets the job done, but lacks fine precision. For more intricate designs, dry etching is preferred. Here, ions or chemically reactive gases are directed at the wafer to remove material. Think of it as laser-guided sculpting, extremely precise but complex. This etching process creates grooves and cavities in the silicon wafer, effectively turning the two-dimensional patterns into three-dimensional structures. What you're left with is a silicon wafer that's not just a blank canvas anymore. It's now a textured work of art, albeit one you'd need a microscope to fully appreciate. Each of these steps gets us closer to a finished microchip, capable of powering the myriad of devices we rely on daily. Chemical vapor deposition. Once the etching has carved out intricate three-dimensional patterns on the wafer, the next step is to fill these patterns with different materials. Think of this like filling in a coloring book, but instead of using crayons, we use atoms. This is where chemical vapor deposition, CVD, comes into play. In the CVD process, various gases are introduced into a chamber containing the silicon wafer. When these gases make contact with the wafer surface, they undergo a chemical reaction and leave behind a solid material, effectively coloring in the etched patterns. There are different flavors of CVD, but they all aim for the same result: a uniform, high-quality film. Plasma-enhanced CVD, for example, uses an electric field to help the gases react more efficiently, ideal for even more complex structures. The materials deposited can vary based on the chip's needs. Sometimes it's an insulating layer, other times it's a conductive metal. Each layer serves a specific function in the final microchip, contributing to its ability to process information or power electronic devices. It's a bit like layering flavors in a complex dish. Each one is crucial for the final taste, or in this case, the chip's performance. What's incredible is that these layers are often no thicker than a few atoms, showcasing the remarkable precision of modern microchip manufacturing. Planarization. Imagine you've just layered a multi-tiered cake. Before adding the next set of layers, you'd want to smooth out the existing ones to ensure an even, stable base. That's essentially what planarization in microchip manufacturing is for. After all the layering and patterning steps, the surface of the silicon wafer becomes uneven due to the deposited materials and the etched patterns. Planarization is the process of leveling this surface to create a flat plane, hence the name. The most common technique used for this is chemical mechanical planarization, CMP. This involves pressing the uneven silicon wafer against a flat, rotating pad soaked in a special chemical slurry. As the pad spins, it grinds down the high spots on the wafer, while the chemical slurry helps to fine-tune the process, ensuring a mirror-smooth finish. Why is this flatness so crucial? Well, any imperfections or unevenness can lead to errors in the subsequent steps of microchip fabrication. Given that we're working at the scale of nanometers, even the tiniest irregularity could throw off the entire chip's function. Through planarization, manufacturers can proceed with additional layers or intricate circuit designs, knowing that they have a perfectly flat canvas to work on. This step might not sound glamorous, but it's essential for the reliable functioning of the final microchip. Ion implantation. At this stage, the silicon wafer's surface is as smooth as can be, but there's more fine-tuning required to turn it into a functional microchip. This is where ion implantation comes into play. It's a process of injecting ions, atoms that have lost or gained electrons, into the silicon wafer to modify its electrical properties. In simpler terms, think of ion implantation as seasoning a dish. Just like adding salt or spices changes the flavor, implanting ions changes how the silicon wafer conducts electricity, enhancing its functionality for specific tasks. To do this, ion implanters accelerate ions through an electric field and shoot them into the silicon wafer. The ions penetrate the surface, settling into precise positions within the silicon's crystal lattice. This level of control is crucial. If the ions go too deep or not deep enough, the microchip won't function as needed. The implanted ions create regions of differing electrical conductivity across the wafer, which is vital for the functioning of transistors, the tiny switches that form the basis of any microchip. These specifically engineered regions allow for the precise control of electrical current, making possible the billions of operations that modern microchips perform every second. Assembly and packaging. Once all the layers have been deposited, the patterns etched, and the wafer polished, it's time to bring our microchip to life in a form that can be used. The wafer is first sliced into individual chips. These chips are then subjected to a series of tests to check for any functional errors. The next step is assembly, where the chip is mounted into a package that allows it to be integrated into a circuit board. Think of this as the chip's protective shell, which often comes with pins or other connectors that facilitate communication with other components. The chip is now almost ready for use, but not before one last critical step: final testing. It undergoes a rigorous set of tests to verify that it meets all performance, quality, and reliability standards. Only then is it ready to be part of the technology that powers our daily lives. After a final inspection to ensure each chip meets the company standards, it's boxed up and prepared for distribution, one step closer to becoming the brainpower behind the multitude of electronic devices we depend on every day.